A lot of new products are set to launch this year, but Elon Musk has been keeping almost everything under wraps because, as you know, if you look at Tesla's history, the things they keep secret are always the most explosive ones. The year 2026 will be a milestone that completely reshapes Elon Musk's empire. No longer just Model 3, Model Y, or the familiar lineup, Tesla is preparing for an all-out assault on segments we've never even imagined. Right now, analysts are focusing their attention on the gigafactories, where new production lines are quietly being installed behind the scenes. If the reports are accurate, we could see at least 5 new models launched this year, many of which Elon Musk has already hinted at. These could be the strategic cards that help Tesla hold on to its crown amid the global surge of electric vehicles. Some of these vehicles are ones you never thought Tesla would build, but by the end of this video, you'll understand why they're incredibly important. So why 2026? And why are these products so exciting? Don't take your eyes off the screen because these are the 5 Tesla masterpieces of 2026 that no one saw coming. Alright, let's get to the first product. While Western media is still busy debating whether the affordable car project has been cancelled to make room for robotaxi, the activity at Giga Shanghai and across Tesla's supplier network in China tells a completely different story. According to the latest reports from component suppliers in Shenzhen and Shanghai, Tesla has quietly restarted orders for a project with the internal code name Project Redwood. Sources within the supply chain say Tesla is working with leading battery manufacturers such as CATL to optimize a new generation of LFP battery cells. The goal is very clear: to cut material costs by up to 30% compared to the current Model 3. This strengthens the belief that a vehicle priced under $30,000, more specifically with expectations around $25,000, is not a far-fetched dream, but a real production plan targeted for 2026. According to us, 2026 is the golden moment for Tesla to launch this model for at least 2 strategic reasons. First, the Model 3, Model Y lineup is showing signs of market saturation, most clearly in China, where some EVs cost only 1/3 of a Tesla's price. For the first time, Tesla has recorded a significant loss of market share under the fierce assault of low-cost domestic EVs, such as the BYD Seagull and the Wuling Bingo. To survive, Tesla is forced to bring out a weapon in this price segment. It may not be able to match Chinese models on price, but it must at least come in below $39,990, the price of the Model Y standard. The second reason is that the unboxed process production line has been completed, and Elon Musk believes this system will allow Tesla to build cars at almost unbelievable speeds, measured in seconds rather than minutes as before. This is the key that analysts believe Tesla will apply to its affordable model. Instead of traditional sequential assembly, this process allows different sections of the vehicle to be built simultaneously and then joined together, reducing factory floor space by 40% and cutting production costs by 50%. Whether we call it the Model 2 or Model Q, suppliers report that the design of this vehicle will be stripped down to the absolute minimum to drive costs as low as possible. Don't expect complex falcon wing doors or premium leather interiors. Instead, we'll see a standard steering wheel and pedals, with all unnecessary details in the cabin completely eliminated. The driving range is also expected to be just over 200 miles per charge, perfect for urban commuting and short trips. The first prototypes of the Model 2 could start appearing as early as Q2 of this year. The second vehicle on this list tackles a problem that is the complete opposite of the Model 2. If the Model 2 is the answer to the cost equation, then the Tesla CyberSUV is the answer to the space equation, a segment that Tesla has unfortunately left wide open. Elon Musk has also hinted at the possibility of such a vehicle being launched, and Tesla has previously leaked early images of this model. Earlier in the Master Plan 4 video released by Tesla, eagle-eyed fans spotted 3 vehicle models subtly hidden on a shelf behind the design studio of Franz von Holzhausen. One of them had the shape of a Cybertruck, but with the rear bed removed and replaced by a long, boxy extended cabin. This design has widely been interpreted as a CyberSUV. Tesla could take the Cybertruck platform along with its 48-volt electrical system and steer-by-wire technology and box it in to create a large 7-seat SUV that's even more spacious than the Model YL. This is exactly how Toyota turned the Hilux into the Fortuner, or how Ford transformed the Ranger into the Everest. Tesla would only need to perform a similar rear-end chop to create an armored-style family vehicle. Tesla may not need to use stainless steel for these models, given the extreme manufacturing cost and complexity. A cast aluminum alloy body with the Cybertruck's angular design language would be far cheaper and significantly lighter. At the moment, the Cybertruck production line is running at only about 30% capacity, roughly 50,000 vehicles per year versus a target of 150,000. Producing a CyberSUV on the same platform would help Tesla fill unused factory capacity and optimize per-unit production costs. While the world is going crazy over full-size SUVs like the Cadillac Escalade IQ or the Rivian R1S, Tesla is stuck with an awkward product lineup. The Model X is too expensive and overly complex with its Falcon Wing doors, while the Model YL is merely a stopgap solution. In reality, their third rows are mostly suitable for children and feel cramped for adults. North American users and large families are craving a true SUV, 3 genuinely spacious rows, generous cargo space, and a look that's impossible to confuse with anything else. That's why we should expect a new CyberSUV to debut sometime this year. Alright, we've now covered an affordable car and a larger family-oriented vehicle. The third model is one that many customers have been waiting for nearly a decade. 2026 will mark nearly a decade since the moment the red Roadster unexpectedly burst onto the stage back in 2017. For the tech-loving community, this wait has gone far beyond the limits of patience. We don't need another flashy unveiling, a presentation packed with unbelievable numbers, or a fake production target announced on April Fool's Day. What the world needs is a car that actually drives on public roads. The Tesla Roadster is not just a car, it is a promise of honor. Even now, many Founder Series customers, those who placed absolute trust in Elon Musk from the very beginning, are still waiting. Remember to secure a spot on the ownership list for this supercar. They had to put down massive deposits of up to $40,000 or even the full $250,000 for the limited edition. In financial circles, these deposits are often jokingly referred to as the longest interest-free loan in history that customers have given to Tesla. The year 2026 must be the moment Tesla repays this debt with a real tangible product, not more tweets and promises. To live up to 9 years of anticipation, the 2026 Roadster is expected to feature technologies that go far beyond today's supercar standards. The most shocking highlight is the SpaceX option package. Elon Musk has repeatedly claimed that the car will be equipped with around 10 small cold gas thrusters mounted around the vehicle. This system would not only allow the car to accelerate from 0 to 60 miles per hour in under 1 second, a figure that breaks the physical limits of conventional tires, but also assist with cornering braking and even enable the car to briefly hover off the ground. With a massive 200 kilowatt-hour battery pack, the Roadster promises a range of up to 620 miles and a top speed exceeding 250 miles per hour. While these specifications sound like science fiction, the pressure on Tesla in 2026 is very real. Competitors such as the Rimac Nevera and the Yangwang U9 have already proven that high-performance electric supercars can be successfully commercialized. If Tesla continues to delay, the Roadster risks going from a leader of the future to a latecomer in the very segment it helped create. Elon Musk has confirmed that a major event could take place on April 1st, but many people remain skeptical, suspecting it might just be another joke from the Tesla CEO. What do you think about this car? Do you believe it will actually reach customers this year? The fourth vehicle on the list of 2026 breakout models is the Tesla Semi Refresh, or Tesla Semi Next Generation. This is not just a minor update, it's a true turning point nearly 8 years after the first prototype was unveiled. Elon Musk has stated that the Tesla Semi will be one of the 3 biggest products of 2026, and the appearance of the Semi Gen 2 at Giga Nevada earlier this month is the clearest proof yet of that claim. With the next-generation Tesla Semi, the most noticeable change is the exterior design. Tesla has brought the design language of the Model Y and Cybercab to this heavy-duty truck. Traditional headlights have been replaced by a full-width light bar across the front, giving the Semi a modern look that aligns seamlessly with the broader Tesla ecosystem. Beyond aesthetics, the new design also improves aerodynamics and eliminates unnecessary elements such as the extended rear side window, glass helping reduce production costs while increasing cabin durability. On the technical side, the biggest leap forward lies in the heart of the vehicle, the battery system. Tesla has confirmed a switch to 4680 battery cells, replacing the LFP packs used in earlier test versions. With nearly double the energy density, Tesla's 4680 cells dramatically reduce overall battery weight while still supporting a 500-mile range. This directly solves the long-standing payload problem, one of the biggest pain points for freight operators. A lighter truck means more cargo per trip, which translates into higher efficiency and stronger profit margins for logistics companies. The energy efficiency of the Tesla Semi Refresh is equally impressive. At just 1.7 kilowatt-hours per mile, it represents a 15% improvement over the previous generation. In the logistics industry, where every single percentage point of efficiency converts directly into cash, this improvement can save fleet operators tens of thousands of dollars per truck per year in electricity costs. Even more disruptive is the Semi's 1.2 megawatt megacharger capability. Recharging 70% of the battery in just 30 minutes effectively erases the traditional downtime advantage of diesel trucks, turning the electric Semi into a true long-haul vehicle. Powering the Semi-Gen 2 is an 800-kilowatt drivetrain equivalent to roughly 1,070 horsepower. Thanks to instant torque delivery, the truck can accelerate smoothly and maintain highway speeds even while hauling 37 tons of cargo up a 5% grade. Tesla has also quietly equipped the Semi with autonomy-ready hardware, including carefully positioned cameras optimized for future self-driving operations. With a new factory coming online, Tesla is gearing up for a production target of 50,000 units per year. The Semi-Gen 2 is no longer a flashy experiment. It is a razor-sharp economic tool ready to eliminate diesel smoke noise and inefficiency from highways around the world. Finally, closing out today's episode, the focus shifts from vehicles to something even more ambitious: Optimus Gen 3, Tesla's humanoid robot. Highly anticipated and closely watched, this next-generation robot is expected to make its debut in Q1, marking another major step in Tesla's broader vision beyond transportation. Based on recent leaks and Tesla's latest moves, there's a very strong chance that Optimus Gen 3 will be the first version to integrate the AI-5 chip, the most powerful heart Tesla has ever built. So why does AI-5 matter so much for a humanoid robot? Think about this. Today's AI-4 already enables Tesla vehicles to process millions of visual data points in real time to drive themselves. But for a robot like Optimus, the computational demands are exponentially more complex. It doesn't just see the road. It has to interact with objects, maintain balance on uneven terrain, and perform delicate human-like hand movements. That's where AI-5 comes in. With performance expected to be multiple times higher than its predecessor, this chip could be the key to transforming Optimus from a flashy demo machine into a robot that can actually do real work. Recently, Elon Musk sent shockwaves through the tech world when he announced that Tesla's AI-5 chip design is almost complete. On X, the Tesla CEO stated, "Now that the AI-5 chip design is in good shape, Tesla will restart work on Dojo 3. But this is only the beginning." Elon Musk also revealed that AI-6 has already entered early development, while laying out a long-term roadmap that stretches all the way to AI-7, AI-8, and AI-9. Musk has confirmed AI-4 by itself will achieve self-driving safety levels very far above human. AI-5 will make the cars almost perfect and greatly enhance Optimus. AI-6 will be for Optimus and data centers, and AI-7, Dojo 3 will be space-based, AI compute. The most shocking part of Musk's message isn't the number of chip generations, it's the 9-month design cycle. In an earlier post, the Tesla CEO wrote, "Our AI-5 chip design is almost done, and AI-6 is in early stages, but there will be AI-7, AI-8, AI-9, aiming for a 9-month design cycle." In the traditional semiconductor industry, launching a new chip generation typically takes 18 to 24 months. Cutting that timeline down to just 9 months is almost unthinkable, especially when even consumer electronics giants like Apple operate on annual cycles that stretch across many years. What this really shows is that Tesla is operating like a software company, even on the most rigid hardware platforms imaginable. If Musk succeeds with this cycle, Tesla could open up a technological gap so wide that competitors like Waymo and even chip giants such as Nvidia would be forced to take notice. We believe this speed is the ultimate weapon. You see, in artificial intelligence, learning ability scales directly with iteration speed. A faster chip production cycle means Tesla can test, fail, and fix faster than anyone else. This compounding advantage creates a powerful economic moat. By the time competitors are just starting to optimize hardware comparable to AI-4, Tesla will already be moving on to AI-6 or even AI-7. The gap in self-driving capability and robot intelligence won't be measured in years anymore. It'll be measured in stacked generations of technology. The AI-5 chip is the perfect successor to AI-4 hardware, but its mission goes far beyond simply running full self-driving in cars. AI-5 is designed to be the unified brain behind all of Tesla's AI-driven efforts. For Optimus, AI-5 enables real-time computer vision models with ultra-low latency. Put simply, one of the biggest weaknesses of today's humanoid robots isn't a lack of raw CPU power. It's that data can't move from memory to the chip fast enough. AI-5 reportedly delivers 5 times the memory bandwidth of AI-4, which could allow Optimus to access massive machine learning models almost instantly. That means the robot no longer has those awkward pause and think moments when it encounters something unfamiliar. Instead, it reacts smoothly, continuously, and intelligently. With AI-5, Optimus doesn't just see the world, it understands it instantly. Ultra-low latency allows the robot to react to sudden human movements in the most natural and safest way possible. In a previous video where Optimus catches a tennis ball, this is the easiest way to understand how AI-5 works. You throw the ball, and thanks to AI-5's ultra-low latency, Optimus can calculate the trajectory and extend its hand to catch it in real time, instead of being one step behind like earlier generation robots running older chips. The motion is precise, smooth, and virtually lag-free. Of course, more powerful chips usually generate more heat and consume more energy. But thanks to an optimized 2nm/3 nm design, Optimus Gen 3 can carry a brain that's up to 5 times more powerful, while still operating continuously for hours, without overheating or rapidly draining its battery. Meanwhile, for Tesla vehicles, AI-5 will enable them to handle complex traffic situations that even human drivers sometimes struggle with. To make the AI-5 vision a reality, Tesla has chosen 2 of the world's leading chip manufacturers, Samsung and TSMC. This is a highly intelligent supply chain diversification strategy designed to secure production capacity at scale. Reports suggest that Samsung is going all in on producing Tesla's AI-5 chips using a 2nm process at its US-based fabs. The company has reportedly accelerated the hiring of highly experienced engineers to tackle the complex technical challenges involved in manufacturing at this node. A 2nm process promises exceptional energy efficiency, allowing Optimus to operate longer on a single charge. Meanwhile, Taiwanese giant TSMC is believed to be responsible for the AI-5 variant built on a 3nm process. Elon Musk has made no secret of his ambition to turn Tesla's in-house chip designs into the highest volume AI processors in the world, a bold statement by any measure. Today, the world depends heavily on NVIDIA for AI data centers. But, with millions of Tesla vehicles already on the road, and potentially millions of Optimus robots in the future, Tesla's internal demand alone could be enough to turn it into a semiconductor powerhouse. At the same time, Musk has cleverly turned these technology updates into a powerful recruiting pitch. He's calling on the brightest minds in the world to join Tesla and help build the most impactful AI brains on the planet. Tesla isn't just selling cars or robots, it's building a full-stack AI infrastructure end-to-end. This may be the biggest change in the history of Tesla's production line and Giga Texas. Elon Musk is preparing to eliminate massive numbers of robotic arms and wipe out a maze of complex components stretching for miles. Tesla has just made a leap that has the entire global auto industry holding its breath by announcing an upgrade to the Giga press at a scale never before seen in the history of mechanical engineering. This is not simply a larger press, it is a technological monster designed to redefine the very concept of efficiency. Imagine this. Instead of assembling hundreds of separate steel parts, this new machine can cast the entire vehicle chassis as a single piece in one press, fast and precise, much like making a plastic toy in a mold. Why is size the key? While Chinese competitors such as XPeng boast about their 16,000-ton machines, Tesla has pushed the limit to an almost unbelievable level, 50,000 tons. With this immense force, Tesla can eliminate thousands of expensive welding robots and dramatically shrink factory floor space. This means production speeds will multiply, with the potential to roll out one vehicle in under 5 seconds, reduce vehicle weight, and most importantly, drive manufacturing costs down to record lows. Is this the secret weapon that will allow Elon Musk to turn the dream of affordable electric cars for every household into reality? Or is it the beginning of the end for the traditional manufacturing methods of legacy auto giants? And how can a machine weighing millions of pounds operate with absolute precision? In today's episode, we're going to dissect the real power inside the 50,000-ton Super Giga press and how it's turning Tesla's factories into true money printing machines, leaving competitors far behind. Let's get started right now.
Like real fast. And then I guess maybe we need to just get even bigger casting machines. Sure, why not? Down, yeah, let's 50,000 tons.
Tesla was the pioneer that brought the gigapress into reality, an idea once considered pure science fiction. But on the other side of the ocean, China has shown that it never accepts second place. When Tesla introduced a 6,000-ton press for the Model Y, China responded with a 7,000-ton machine. When Tesla upgraded to a 9,000-ton press for the Cybertruck, XPeng shocked the world with its 16,000-ton hypercasting machine, which is currently regarded as the largest on the planet. However, Elon Musk never plays a game on equal footing. Tesla's answer is the 50,000-ton giga press. With a clamping force of up to 500,000 kilonewtons, it is 3 times more powerful than Xpeng's beast. While Xpeng's machine can only cast individual sections of a chassis, Tesla's super machine is designed to cast 5 vehicle chassis at the same time. This is the move that allows Tesla to pull far ahead of its rivals, with production speeds measured in seconds. One common misconception needs to be cleared up. 50,000 tons is not the weight of the machine, but the clamping force it generates. With pressure reaching up to 500,000 kilonewtons, this machine is more than 3 times as powerful as Xpeng's system. This enormous force allows Tesla to use much larger molds that can hold more molten aluminum, producing parts that are not only bigger, but also thicker and far more structurally complex. The difference comes down to a staggering number. While Xpeng's 16,000-ton machine can cast only 1 chassis per cycle, the 50,000-ton gigapress can cast at least 5 vehicle chassis at the same time. This explains why Elon Musk is confident in claiming that a car can roll off the production line in under 5 seconds. Take Xpeng's 16,000-ton hypercasting machine as an example. It delivers around 160,000 kilonewtons of clamping force, strong enough to cast massive components like the front and rear underbodies of an EV. Xpeng already uses this system to produce the P7 Plus, and it has allowed the company to collapse thousands of individual parts into just 2 large castings. Now scale that up to a 50,000-ton press. That kind of machine is expected to generate roughly 500,000 kilonewtons of clamping force, more than 3 times what Xpeng's setup can deliver. As mentioned earlier, force at that level could allow Tesla to die cast an entire unibody structure, like the one envisioned for the Cybercab, in a single shot. More clamping force doesn't just mean bigger parts, it means bigger molds, more molten metal, and the ability to create components that are thicker, stronger, and far more structurally complex. Pinning down the exact weight of these machines isn't easy since there's no official data yet for presses of this size, but we can make some educated estimates by looking at earlier models. The 6,000-ton giga press, for example, is confirmed to weigh about 430 metric tons, or roughly 948,000 pounds. A 9,000-ton version would likely come in around 688 tons, or about 1.52 million pounds. Using that progression, Xpeng's 16,000-ton hypercasting machine likely weighs at least 1,200 tons, around 2.6 million pounds, and takes roughly 120 days to fully assemble. If we follow that same logic, a 50,000-ton gigapress could weigh an absurd 8.16 million pounds. That number is honestly hard to even process, and when it comes to sheer size, the 16,000-ton version already looks like a mechanical monster, which explains why it takes about 4 months just to assemble. While we don't have exact dimensions for that machine, we do know the 6,000-ton gigapress measures roughly 64 feet long, nearly 20 feet wide, and about 17.4 feet tall. So yeah, the 50,000-ton press is going to be on a completely different level. We're talking about something roughly the size of a 3 to 4-story building laid on its side. Tesla would likely need to construct an entirely new facility just to house it, complete with ultra-deep reinforced concrete foundations to handle the weight. For perspective, a 50,000-ton giga press would generate about 8.3 times the clamping force of the 6,000-ton version, and roughly 5.5 times more than the 9,000-ton press. Early estimates suggest dimensions in the neighborhood of 131 feet long, 42 feet wide, and nearly 39 feet tall. At that scale, it's no surprise installation alone could take up to 6 months. That said, despite all that power and size, the core operating principles aren't drastically different from the 16,000-ton gigapress. First, the process still begins with material preparation. Tesla melts down new aluminum ingots along with the leftover aluminum from previous casting cycles in a furnace heated to around 850 degrees Celsius. As far as we know, the gigapress uses a 2-furnace system to handle the aluminum alloy. One furnace, used for melting, is gas-fired and runs at about 850 degrees Celsius. The other holds the already molten metal and is electrically heated, keeping the temperature between 750 degrees Celsius and 850 degrees Celsius. The empty space inside the holding furnace is filled with nitrogen gas, which prevents oxidation in the molten aluminum and helps maintain a stable temperature. Operators also use argon gas and a silicon carbide filter to remove impurities and particles larger than 25 microns. That's the material prep phase. Next up, mold preparation. Before each cycle, the giga press lubricates the mold surface. A robot sprays about 35 milliliters of soybean oil in a thin, even layer, kind of like applying non-stick spray to a baking pan, making it easier to release the cast part later on. Then, a vacuum system removes any air, and the molten aluminum is transferred from the holding furnace to the giga press's injection chamber. There, the liquid metal is injected into the mold cavity by a high-speed piston, which is also lubricated with about 8 milliliters of oil before each shot. After the aluminum is injected, it remains in the mold until it solidifies. The cast part is removed from the mold at around 400 degrees Celsius. It's then placed in a cooling tank to rapidly bring its temperature down from 400 degrees Celsius to about 50 degrees Celsius. This quick cooling helps eliminate certain defects and improves the material properties. Finally, the mold is opened, cooled to around 185 degrees Celsius, and thoroughly cleaned by a robot to prepare for the next cycle. The next casting cycle typically begins 1 to 2 minutes after the current one ends. According to Elon Musk, to make this possible, Tesla had to design an ultra-advanced cooling system inside the giga press. The 50,000-ton giga press is also equipped with a smart mold separation mechanism and a much more advanced AI-powered quality inspection process compared to previous models. Even if competitors have a 50,000-ton press, they can't replicate Tesla's proprietary method. That's what sets it apart. Excess metal is trimmed off and recycled for the next melt. The final part undergoes X-ray inspection to ensure structural integrity and quality. One of the biggest challenges during the casting process is keeping the mold from popping open under the intense pressure of the molten aluminum injection. That's why the machine must generate an extremely high clamping force to keep the mold sealed shut. And with the 50,000-ton giga press, that clamping force is absolutely massive.
In a single casting machine, we could do like 5 at a time or something, you know? I'm trying to think, like, how do you scale castings? Because you got liquid metal, metal's got to cool, and then you've got to automate, getting all the bits and pieces off the casting so it's usable.
According to Elon Musk, a 50,000-ton gigapress can cast at least 5 EV chassis in a single shot, something XPeng's 16,000-ton hypercasting technology cannot achieve. Elon Musk explained that the 50,000-ton machine can handle a massive volume of molten metal, casting multiple chassis simultaneously. It then cools the metal and automatically trims excess material, producing a finished part with minimal manual intervention. With a clamping force of 500,000 kilonewtons, this machine can use larger molds that hold enough metal to create several components at once, significantly boosting production speed and cutting costs. In contrast, XPeng's 16,000-ton hypercasting machine, with its 160,000 kilonewtons of clamping force, can only cast one chassis at a time. Its limitations lie in mold size and pressure, which are insufficient for simultaneous multi-part casting. However, the 50,000-ton gigapress will require ultra-efficient cooling systems and highly complex automation to maintain quality standards. In fact, the larger the die casting machine, the higher the precision. Molten aluminum is injected into the mold at incredible speed, and the process must ensure the metal fills every section of the mold evenly and completely before cooling and hardening into a solid structure. On a 6,000-ton gigapress, around 80 kilograms or 176 pounds of molten aluminum is shot into the cold chamber at 10 meters per second. But with the 50,000-ton gigapress, the volume of aluminum is significantly higher, and the injection speed must be even faster. This process demands extreme precision. Too fast, and air bubbles may form. Too slow, and the aluminum could start to cool before fully filling the mold. The truth is, bringing the gigapress to Tesla was no easy feat. The machine Elon Musk envisioned was almost like a technology ahead of its time, a needle in a haystack. Building such a machine had never been done in the auto industry before. At the time, car manufacturing primarily relied on steel stamping and robotic welding, involving hundreds of parts and complex processes. So naturally, most die-casting machine manufacturers were skeptical about the feasibility of Musk's idea. Elon Musk initially reached out to 5 major die-casting manufacturers. All of them quickly turned down the proposal. It seemed like the idea might be dead, until, as a final gamble and Tesla's last hope, Musk contacted a 6th company, Hydra. And finally, Hydra gave Tesla the answer it desperately needed. It's possible. For Musk, even a maybe at that moment meant everything. To rapidly turn the giga press into a reality, Tesla worked closely with Hydra for over a year. The development process was far from simple. Tesla continuously requested design changes, forcing Hydra to adapt its machines accordingly. One Hydra representative shared that every time Tesla proposed a modification, their engineering team had to work around the clock to update the design. In the end, the giga press was born, and it was a success. So how much does each version of the giga press cost? The cost of giga press machines is a critical factor in determining whether high-pressure die casting can be widely adopted in the automotive industry, especially for EV production. Based on reports we've found, the 6,000-ton giga press is priced at approximately $6.48 million. With a clamping force of 60,000 kilonewtons, this version is suitable for smaller-scale projects with a lower initial investment, though its production capacity is more limited. Next is the 9,000-ton giga press, which costs between $9.72 million and $11.34 million. It delivers a clamping force of 90,000 kilonewtons, making it capable of casting more complex components, such as integrated chassis for mid-sized vehicles. For the 16,000-ton Xpeng hypercasting, the cost is reported to range from $17,280,000 to $21,600,000. For the 50,000-ton giga press, the estimated price could range from $43,200,000 to $64,800,000. With a clamping force of 500,000 kilonewtons allowing for the casting of 5 chassis at a time, the machine requires advanced cooling technology, complex automation systems, and giant molds, pushing up production costs. Compared to the 16,000-ton machine, the price of the 50,000-ton machine can be 2 to 3 times higher, which is a trade-off for Tesla to produce faster and turn a profit sooner. So why do these machines command such a high premium? The staggering price of a gigapress is driven by more than just its physical size. First and foremost is the precision engineering of the clamping system. To cast a single piece of aluminum the size of a mattress, the machine must apply tens of thousands of kilonewtons of force to keep the die closed while molten metal is injected at high speed. Any microscopic gap during the injection process would result in flash or structural defects, rendering the multi-thousand-dollar casting useless. Secondly, the cost is heavily influenced by the ancillary ecosystem. A gigapress does not operate in a vacuum. It requires a specialized melting furnace, robotic arms for part extraction, and advanced X-ray cooling stations to inspect internal structural integrity. Furthermore, the molds dies themselves are a massive expense. A single set of high-durability steel dies can cost between $1.5 million and $2.5 million. These molds must withstand extreme thermal cycling, heating and cooling thousands of times per day without warping or cracking. While the upfront capital expenditure is daunting, the long-term operational savings provide a compelling justification for the price. Traditionally, a vehicle's rear underbody is composed of 70 to 100 separate stamped steel parts. Assembling these requires an army of roughly 600 specialized robots for spot welding, riveting, and gluing. By investing $10 million in a single gigapress, a manufacturer can replace that entire section of the assembly line with one machine and a few robotic handlers. This unboxing of the manufacturing process reduces the factory footprint by up to 35% and drastically cuts labor costs. Furthermore, by using specialized aluminum alloys that do not require heat treatment, manufacturers save on energy and time. In this context, the gigapress is not just a tool, it is a financial instrument designed to lower the cost per car over the life of a vehicle program. For companies like Tesla and Hydra's other clients, the multi-million-dollar price tag is a necessary entry fee to achieve the margins required to make electric vehicles affordable for the mass market. The 50,000-ton Tesla gigapress isn't just a massive machine, it represents an entirely new chapter in automotive manufacturing. With the potential to cast up to 5 vehicle bodies at once, it doesn't merely reduce production time and costs, It blows past the traditional limits of chassis casting altogether. Compared to XPeng's 16,000-ton hypercasting system, which can only produce a single frame per cycle, Tesla is setting a completely new standard for scale, speed, and efficiency. And, to be clear, hypercasting itself is a major step forward for China's auto industry. But when you look at automation, production line integration, and Tesla's ability to optimize vehicle structures through software, the 50,000-ton giga press is playing in a different league. This isn't just about building a bigger machine, it's about redefining manufacturing from the ground up. Programmable unibody designs, simplified supply chains, and production systems that can adapt in real time. What truly gives Tesla an edge isn't size alone, it's the pace of innovation and the level of control Tesla maintains across the entire stack, from software and hardware to logistics and factory operations. While companies like XPeng are still experimenting with hypercasting at a pilot scale, Tesla is already turning radical ideas into production-ready reality, with global scalability in mind. Just as Ford's assembly line reshaped the auto industry and Toyota's lean manufacturing transformed global production standards, Tesla's 50,000-ton gigapress is redefining what's possible for electric vehicles. At this point, the real question isn't who will catch up, it's who's willing to push manufacturing this far, this fast. Flying cars have been promised for decades. From magazine covers in the 1950s to glossy concept videos in the early internet era, the idea has always sounded just close enough to feel inevitable. Anyone who has ever been stuck on a highway crawling along at 2 miles an hour has probably had the same thought. Why not just lift off and fly over the mess? That fantasy has been reinforced for generations by movies, books, and popular culture. And yet, after more than half a century, most people have never seen a flying car outside of a prototype or a carefully staged demonstration. That long gap between promise and reality raises a more serious question. If flying cars were always such a good idea, why did they fail for so long? And just as importantly, why are they suddenly getting serious attention now, with real companies investing hundreds of millions of dollars instead of just producing concept art? To answer that, it helps to start with a reality check. The core problem was never imagination. Engineers have been able to make vehicles leave the ground for decades. The problem was everything else. Energy density, for example, has always been a brutal constraint. Gasoline contains roughly 12,000 watt-hours of energy per kilogram. Modern lithium-ion batteries, even today, typically deliver around 250 to 300 watt-hours per kilogram at the pack level. That is a gap of nearly 2 orders of magnitude. How do you lift a vehicle vertically when your energy source is both heavy and limited? And how do you do it safely, repeatedly, and at a cost that makes any economic sense? This is where the shift toward electric propulsion begins to matter, but also where its limits quickly appear. Electric motors are far simpler than combustion engines. They have fewer moving parts, respond almost instantly, and can be distributed across a vehicle. Instead of one large engine, a flying vehicle can use 8, 10, or even 12 smaller motors. That improves control and adds redundancy. If one motor fails, others can compensate. But redundancy does not come for free. Vertical takeoff demands enormous bursts of power. Many eVTOL-style designs require several hundred kilowatts just to get airborne. The obvious question then follows: how often can you subject a battery pack to those high power cycles before degradation becomes a major operating cost? Looking at real companies helps ground this discussion in something more concrete. Take Klein Vision and its aircar. Instead of vertical takeoff, it uses a fixed-wing design and requires a runway, dramatically reducing energy demands. That immediately solves one problem. It avoids the worst battery limitations of vertical lift, but it introduces others. The aircar must comply with both automotive and aviation regulations, two regulatory systems that were never designed to overlap. Structurally, the vehicle needs to remain light enough to fly efficiently, on the order of roughly 1 metric ton while still surviving road impacts and meeting crash standards. Mechanically, the folding wing system adds complexity that must work perfectly every time. Klein Vision has demonstrated multiple successful test flights, which is no small achievement. But can a design like this scale beyond small production runs? And can it do so at a price point that appeals to more than a narrow niche of buyers? XPeng approaches the problem from a different direction. As a major electric vehicle maker, XPeng has explored vertical takeoff concepts aligned with the broader urban air mobility movement. On paper, this looks logical. XPeng already has experience with electric drivetrains, power electronics, and software. but vertical flight changes the economics and physics of transportation. Hovering is inherently inefficient compared to forward flight. As a result, many current eVTOL prototypes target practical ranges of around 20 to 30 miles, sometimes less once real-world conditions are considered. Is that range sufficient to justify the cost of infrastructure, certification, and operation? And what happens when battery packs, often costing tens of thousands of dollars, need replacement after a few thousand high-power cycles? Then there is Aleph Aeronautics, which has attracted attention for promoting a vehicle that looks like a conventional car but can take off vertically by rotating its internal structure. The appeal is obvious, a flying vehicle that fits within existing road infrastructure. But this concept highlights one of the deepest tensions in the entire flying car idea. Cars are designed to maximize traction, durability, and crash safety. Aircraft are designed to minimize weight, reduce drag, and generate lift efficiently. Can one vehicle truly satisfy both sets of goals, or does it inevitably become a compromise? Aleph's publicly discussed flight range and payload numbers remain modest, which does not make the idea meaningless, but does frame it as a very specific solution rather than a universal one. These examples point to an uncomfortable but important reality. Flying cars are not blocked by a single missing breakthrough. They are constrained by many small limitations that stack on top of each other. Battery energy density, thermal management, noise, certification, maintenance, insurance. Consider noise alone. Even electric rotors generate significant sound, especially during the takeoff and landing. Urban noise regulations are far stricter than most people realize. Can flying vehicles operate frequently over dense neighborhoods without provoking public backlash? And if they cannot, where exactly do they fit into the transportation system? Economics adds another layer of complexity. Helicopters already exist and solve many of the same problems flying cars aim to address. But helicopters are expensive to buy, expensive to maintain, and require highly trained pilots. Electric flying vehicles promise lower maintenance and eventually higher levels of automation. But those savings must offset battery replacement costs, charging infrastructure, regulatory compliance, and insurance. This is why most serious companies have quietly moved away from the idea of selling flying cars to everyone. Instead, they talk about fleets, services, and controlled routes. Not mass adoption, but selective deployment. Does that make flying cars less revolutionary, or simply more realistic? Regulation ultimately shapes everything. Aviation safety standards are far more demanding than automotive ones. A car can break down safely by pulling over. An aircraft cannot. In aviation, failure is a life-threatening event, not only for passengers, but also for people on the ground. That is why certification takes years, not months. In 2019, European regulators introduced special certification conditions for VTOL aircraft carrying up to 9 passengers with a maximum takeoff weight of about 7,000 pounds. That move signaled something important. Regulators were beginning to adapt to a new category of aircraft. But adaptation does not mean approval is easy, fast, or guaranteed. So when people ask why flying cars are suddenly being taken seriously, the answer is not that the dream has suddenly become easy. It is that the conversation has become more honest. Electric propulsion, modern software, improved materials, and better manufacturing have removed some barriers, but not all. Companies like Klein Vision, XPeng, and Aleph Aeronautics are not chasing fantasy. They are navigating trade-offs. And those trade-offs explain both the renewed interest and the persistent skepticism. Which leads to the more useful question. Not will flying cars replace cars, but where do they actually make sense? How many flights per day would justify the cost? How much time must be saved to offset higher prices? And how much complexity are cities and regulators willing to accept? Flying cars have not arrived as a mass market reality, but they have crossed a more subtle threshold, from being dismissed outright to being examined seriously. And in technology, that shift alone is worth paying attention to. If flying cars are this complex, constrained, and expensive to build, a reasonable question naturally follows. Why are companies still pursuing them? And more importantly, how could something so costly ever become a profitable business? The answer lies not in mass adoption, but in pricing, utilization, and the kind of transportation problem flying vehicles are actually meant to solve. To begin with, it helps to look at real prices rather than optimistic forecasts. Basic roadable aircraft such as the Samson Switchable are priced around $170,000. More advanced vehicles capable of transitioning between road and air regularly sell for far more. High-end flying cars and car-aircraft hybrids typically fall between $500,000 and well over $1 million. The two-seat air car, for example, has been estimated to cost anywhere from roughly $500,000 to about $1.1 million, depending on configuration and production scale. A separate analysis conducted in the United Kingdom found that the average purchase price of a flying car was approximately £495,000, or around $630,000 US, before licensing fees and additional costs were even considered. That immediately places flying cars in a completely different financial category from conventional automobiles. A $35,000 sedan or even a $100,000 luxury car is simply not a meaningful comparison. Flying cars are closer, economically speaking, to light aircraft than to road vehicles, and that is not an accident. They are built to aviation standards, not automotive ones. The materials, redundancy, testing, and certification requirements are far more demanding. The question then becomes, are these prices a permanent barrier, or are they a reflection of early-stage technology? Supporters often argue that today's prices reflect early production volumes, and that costs could fall significantly with scale. Some projections suggest that prices might eventually decline into the $150,000 to $250,000 range as manufacturing matures. But those projections usually come with an important caveat. That scenario is many years away. In the near term, flying cars remain capital-intensive machines built for early adopters, not for the mass market. And price is only the beginning of the cost story. You cannot simply buy a flying car and start using it. Training and licensing add a substantial upfront expense. Estimates from the UK suggest that pilot licensing and training alone could cost around $35,000. That is equivalent to buying another new car, simply to learn how to operate the first one. Is that unreasonable? Not really. You are not just driving. You are flying an aircraft. But it does change the economics. It raises the barrier to entry and narrows the pool of potential private owners even further. Operating costs add another layer of complexity. Maintenance costs for eVTOLs and flying cars remain uncertain because only a small number of vehicles are currently in regular use. Electric propulsion does reduce some mechanical maintenance compared to combustion engines, but aviation-grade components, battery replacements, specialized inspections, and dual certification requirements all carry significant costs. Early estimates for total operating cost in high-utilization urban air mobility scenarios suggest figures around $2.97 per passenger seat mile. Importantly, that number includes both acquisition and operating costs, not just routine maintenance. When analysts isolate direct operating costs, estimates vary widely. Some feasibility studies for electric aircraft suggest operating costs as low as 25 to 75 cents per mile flown. But those figures typically exclude fixed costs, such as insurance, storage, and certification. Other analyses estimate costs closer to $3.50 per mile once all factors are considered. Early projections for eVTOL air taxi services place per-passenger mile costs anywhere from about $2.25 to as high as $11, depending on utilization, energy prices, and maintenance assumptions. These numbers are not trivial. So why would anyone think this makes economic sense? The answer lies in how flying vehicles are expected to be used. Profitability does not depend on selling millions of vehicles. It depends on keeping a smaller number of vehicles flying as often as possible. This is the same logic that governs commercial aviation. An aircraft that flies 1 hour a day is a financial failure. An aircraft that flies 10 hours a day can be profitable even if its purchase price is high. The same principle applies here. Flying cars and eVTOLs are not designed to sit idle in personal garages. They are designed for fleets, routes, and high utilization. This is where the value proposition becomes clearer. Flying vehicles are not competing with economy cars. They're competing with time. A 20 to 30 mile trip that takes 90 minutes on congested roads might take 10 to 15 minutes in the air. For certain passengers, business travelers, medical transport, time-critical logistics, that time savings has real monetary value. The question is not whether everyone will pay for it, but whether enough people will. Energy costs further support this model. Studies of electric aircraft suggest energy costs as low as $8 to $12 for a 100-mile flight, compared to roughly $400 in fuel for a conventional aircraft covering the same distance. That difference is substantial. While these figures do not include all costs, they highlight why electric propulsion is so attractive. If energy remains a small fraction of total operating cost, then improvements in battery technology and charging efficiency directly improve margins. Still, it would be misleading to suggest that flying cars are on the verge of becoming cheap. Even optimistic scenarios suggest that per-passenger mile costs might eventually fall to around $1.50 in mature urban air mobility systems. That is competitive with premium ground transportation, not with everyday commuting. And that distinction matters. Flying cars are not about replacing cars. They are about serving specific high-value routes where speed matters more than cost. So why are companies willing to invest billions collectively into this space? Because the upside, while narrow, is significant. If even a small percentage of urban trips shift to air, the revenue potential is enormous. Analysts estimate the global urban air mobility market could approach $1.5 trillion by 2040. That figure assumes selective adoption, not universal use. It assumes fleets, not garages. And it assumes prices remain high enough to support the infrastructure required to operate safely. This brings us back to price. High prices are not a flaw of flying cars. They are a prerequisite. Certification alone can cost tens or hundreds of millions of dollars. Redundancy requirements add hardware. Insurance costs reflect aviation-level risk. Batteries must be replaced periodically. All of this demands pricing that reflects reality, not consumer expectations shaped by the automotive market. So when critics point to six-figure or seven-figure price tags and declare flying cars a failure, they may be asking the wrong question. The more relevant question is whether a limited number of expensive vehicles, operated intensively, can generate enough revenue to justify their costs. History suggests this is possible. Helicopters already do it, albeit imperfectly. Flying cars and eVTOLs are an attempt to improve on that model, not to democratize flight overnight. In that sense, flying cars are not a consumer product waiting to get cheaper. They are an aviation service waiting to become efficient. And whether they succeed will depend less on how low prices fall and more on how well companies manage utilization, regulation, and public acceptance. That is where the real profit or loss will be decided. Looking ahead, the future of flying cars is best understood not as a sudden breakthrough, but as a gradual progression through clearly defined phases. Over the next 5 to 10 years, the industry is likely to remain focused on proof rather than scale. The immediate priority is not mass deployment, but certification, safety validation, and controlled operations. In this phase, flying vehicles will appear only in limited environments, airport to downtown routes, medical transport corridors, and highly regulated urban zones. This is the expensive stage. Capital will be consumed faster than revenue is generated, and most projects will not survive. That outcome is not a failure of the concept. It is a normal filtering process in aviation. If this first phase succeeds, the next stage, the early 2030s, will be defined by standardization rather than expansion. This is when regulators, operators, and manufacturers begin to agree on common rules: noise thresholds, air corridors, vertiport designs, and operating procedures. Costs will not collapse, but they will stabilize. Flying vehicles will increasingly be treated as infrastructure-backed services rather than experimental machines. Importantly, this is also when the industry will stop talking about ownership almost entirely. The dominant model will be fleet-based, with utilization, not unit sales, determining success or failure. Beyond that, in the longer term, flying cars are likely to scale geographically rather than socially. They will expand into cities where congestion, geography, and economic density justify their existence. Mountainous regions, island clusters, megacities with saturated ground infrastructure, these are the environments where urban air mobility makes sense. What they will not become is a universal consumer product. There will be no flying car in every garage. Airspace, noise, safety, and regulatory complexity make that vision unworkable, regardless of technological progress. Flying cars are not waiting for a single breakthrough or a single visionary to make them real. They are waiting for alignment between technology, economics, regulation, and public acceptance. That alignment takes time. And the companies watching most closely are also the ones moving most carefully. Are flying cars a serious next step in transportation, or another expensive solution searching for a real problem? And if even companies like Tesla are staying out, does that signal caution or simply a missed opportunity?